This is going to be a video lecture on the introduction to statistical inference. So we'll be doing this instead of the classroom lecture that was supposed to be scheduled today, Wednesday, the 11th of March, 2020. So we start off with defining what statistical inference is. So it's defined by Daniel and Cross in their textbook as the procedure by which we reach a conclusion about a population on the basis of information contained in a sample that has been drawn from that population. So what this sentence is basically saying is that if we want to measure something about a population, we have to consider that the population is vast and large, and measuring the particular characteristic of interest in each and every member of that population is very much infeasible, and there will be a lot of expense associated with it. So instead of measuring everyone in the population, we are just going to draw a small sample, or at least a sample of that population, which we assume or which we make sure is representative of that sample. And then we measure the characteristic of interest in that sample that we've drawn from the population. And then with the data that we'll be getting from the sample, we will be making inferences as to what the measure of that particular characteristic is and project it to the population itself. So basically, statistical inference, or rather inferential statistics, really is the analysis that infers or deduces properties about a population, making use of a sample or a small sample that was drawn from that population. Now, statistical inference will include hypothesis testing, which will be in the next video. For this video, we'll be deriving what we call estimates. So we'll get to that later on. Now, before we continue, let me just define two new terms, or these are actually terms that are frequently used as far as statistical inference is concerned. That would be the parameter and statistic. So a parameter is defined as an unknown measure that describes the entire population. Now, it's unknown because, of course, populations are typically large, and you're unable really to measure each and every single person of that population. So basically, the parameter or the measure of that characteristic for that particular population remains unknown. Now, on the other hand, a statistic is an estimate of that parameter, and then we obtain data from, or we obtain a statistic by measuring a sample, okay, which we have drawn from the population itself, and we're assuming that sample to be representative of that population. Now, a parameter is a numerical constant because this is basically the measure that was taken from every single person of the population. But because of the infeasibility of doing such, of course, that particular constant remains unknown. Now, with statistic, on the other hand, of course, there are many ways in which you can draw a random sample from the parameter. So a statistic would vary every time you draw a different sample from the population concerned. So basically, a statistic is not constant because of that, but rather variable depending on the random sample that you've drawn from that particular population. Now, we call this variation as sampling variation. Now, let me expound more on the definition of statistical inference. So you have, for instance, a target population, and typically such populations are so large that it's really impossible to measure the characteristic of interest in each and every single member of that population. So what the researchers do instead is they draw a random sample, which is definitely much smaller than the target population, from that population itself. Now, then the researchers would then measure the characteristic of interest from that sample that was drawn. So basically, they generate numerical data from that sample, which we use to obtain the pertinent statistic, which we just defined in the previous slide. And then using the statistic, uh, we try to estimate or test hypotheses regarding unknown parameters or the unknown parameter of interest of the target population. And with that, we're able to draw conclusions about the target population based on the data that we've drawn or based on the data that we've obtained from the random sample that was drawn from the original target population. Now, statistics or parameters can be what is listed here in this slide, but they're not limited to that. So we'll be talking more about mean, proportion, the differences between two means, the differences between two proportions, variance, SD, and correlation, more in the upcoming videos. There will be at least another video on this one, and I'll be showing you how to do the t-test, do the chi-square test using a free downloadable statistical software called JASP or JASP. So I'll be mentioning more about that in the next video lecture. Okay, so now again, more on making inferences about a population. So basically, we want to know something about the population, but because that population is so large, all we can do is really to select a random sample from that population, assuming that that particular sample is a representative of that population. So we only have a small sample that we can work with. So we obtain the statistic from the sample, and from that statistic that we obtain from the sample, we make inferences about the unknown population parameter. So basically, we're making conclusions about a vast population based on a random sample that we've drawn from that population. Okay, so again, it goes to show also that whichever that random sample is, we have to make sure that that random sample is representative of the population at large. Next, we talk about estimation. So recall from earlier that statistical inference also includes hypothesis testing, which I'm going to talk about in the next video, and deriving what we call estimates. So to define what an estimate is, or rather to define what estimation is the rough calculation of a value, number, quantity, or extent of something. So it's not exactly the same value, the same actual value, but just a rough calculation of it. So basically, if we're making an estimation, we have a set of possible values or a range of possible values that we're thinking the actual value might be contained in. Okay, so in biostatistics, it is the process by which a statistic, which you've drawn from the random sample, is used to approximate, which we call estimation, of the corresponding parameter of the population. So this is basically what I've been explaining for the past couple of slides. Okay. Now there are actually two methods of estimation. So the first one is coming up with a point estimate. So when we say point estimate, it actually refers to a single number that we gauge as the best guess of the population parameter, which is unknown. Now, the problem with this one is with a single number, we don't know how close that particular estimate is likely to be to the population parameter. Now, to circumvent this problem, we actually come up with a range of possible values within which the unknown population parameter is most likely going to lie in. And we call that type of estimation interval estimation. So we come up or we estimate a range of values within which the true population parameter lies with high probability. Now, it's actually more useful compared to your point estimate because it incorporates a margin of error which helps us gauge the accuracy of the point estimate. Now, we very often report point estimate along with its interval estimate. Okay, and that interval estimate we very often refer to as the confidence interval. So a lot of you may have encountered this phrase before when you had your undergrad biostatistics subjects. Okay, now just to reiterate, so a point estimate is a single number, and the confidence interval is that range that provides additional information about the variability of the point estimate. Okay, so it's within this confidence interval where the population parameter is most likely going to lie in. Okay. Now, oftentimes you'll hear confidence intervals being described as, let's say, 90% or 95% or 99% confidence interval. Now, in medical research, we default usually to 95% confidence interval. Now, this actually corresponds to what's called a z deviate of 1.96, which also corresponds to the very often heard alpha error of 0.05. Okay, so we will be talking about alpha and beta errors in the next lecture. So for now, what you really need to understand, or at least to remember, is that the default that we use in medical research is the 95% confidence interval. It corresponds to an alpha error of 0.05 and a z-deviate of 1.96. Now, as you, or if you desire a wider confidence interval, then you will have to increase your sample size requirement. Now, we need to clear certain misconceptions regarding the confidence interval. So again, we have here 95% confidence interval. That's the default that we go to with medical research. Now, at first glance, the 95% part here seems to represent a probability. That's actually wrong. So the more accurate way to describe confidence interval is, let's say you have a population and you drew a sample randomly. You got the statistic or the statistic measure of that sample. You computed the corresponding 95% confidence interval. You put back that sample in the population, draw another sample again, measure the statistic, get the corresponding confidence interval, put that sample back in the population, and then you do that 100 times. So 95 when with 95% confidence interval, it means that 95 of the 100 generated confidence intervals would contain the population parameter. So that's actually the more correct way of regarding confidence interval. Now, that being said, it's wrong to say that 95% here represents a probability. So, as I mentioned earlier, it does not represent a probability, nor does it represent any particular chance. So, here it's wrong to say there's a 95% chance that the true population value lies within this interval. Now, rather, we say that we are 95% confident that the true population value lies within the interval. Okay? So the confidence here does not really talk about the interval per se, but rather the process that generated it. So again, recall the 100 times that you drew a sample from the population, and every time you drew a sample, you measured the statistic and you generated a confidence interval from it. Okay. Now, this one you don't need to really worry about the formulas or how to obtain it because the software will be doing that for you. So it's just I just would just like to mention that the way we compute the confidence interval for means or averages is different from when we compute proportions. So we'll actually be going back to means and proportions when we go to the next video, when we talk about the t-test, the chi-square test. It's basically hypothesis testing, which we'll be covering in the next video. So I'll be ending this short lecture here, and Dr. Alviar will also be providing to you supplementary materials that we urge that you read, because I'm not really sure how much of it would actually be included in the exam. So, okay, so I'll be ending it here.